sklearn, utils, class weight, computes sample weight. Description. This function calculates sample weights for imbalanced datasets. It helps to address class imbalance by assigning higher weights to samples from underrepresented classes, effectively giving them more influence during model training. Inputs. Class weight: a dictionary with keys representing class labels and values representing their weights. If balanced, it automatically calculates weights inversely proportional to the class frequencies. Y. The target variable is a 1D array or list, representing the true class labels of the samples. Outputs. Sample weight: a 1D array of weights assigned to each sample, reflecting the class imbalance. Steps. Calculate class frequencies. The function first determines the frequency of each class in P. Provided target variable Y. Calculate weights if class weight is balanced. The weights for each class are inversely proportional to their frequencies. Otherwise, the weights specified in the class weight dictionary are used. Assign weights to samples. The calculated weights are then assigned to each sample based on its corresponding class label. Metrics. F1 score. This metric measures the balance between precision and recall. Often used in imbalanced datasets. AUC area under the curve, a metric for evaluating the performance of binary classifiers. Useful for imbalanced data as it considers the ranking of samples. Visualization plots. Class distribution plot shows the distribution of samples across different classes, highlighting the imbalance. Precision recall curve plots precision against recall at various thresholds, providing insights into the model's performance on different class balances. Fine-tune parameters. Class weight. This parameter determines how sample weights are calculated. Experiment with different values, e.g., balanced. Custom dictionary to optimize for the specific dataset. Uncertainty methods. Confidence intervals. Calculate confidence intervals around the model's predictions to assess the uncertainty associated with each prediction, especially for minority classes. Bootstrap resampling. Repeatedly sample data with replacement to estimate the variability of the model's performance and identify influential samples. Challenges and fixes. Challenge 1. Overfitting to the majority class. If weights are not adjusted correctly, the model may overfit to the majority class, resulting in poor performance on minority classes. Sample use case. In a medical diagnosis dataset with a high prevalence of healthy patients, the model might learn to predict healthy outcomes accurately but fail to identify rare diseases. Fixes. Use balanced class weight. This automatically assigns higher weights to minority classes, reducing overfitting. Fine-tune the class weights. Experiment with custom weight values in the class weight dictionary to find the optimal balance. Challenge 2. Difficulty in evaluating model performance. Standard metrics like accuracy can be misleading in imbalanced datasets. Sample use case. A model with high accuracy but low recall for the minority class might not be useful in applications where detecting minority instances is crucial. Fixes. Use appropriate metrics. Focus on metrics like F1 score, AUC, or precision recall curves to assess the model's performance on minority classes. Use stratified cross-validation. Ensure that the distribution of classes is maintained in each fold of cross-validation to obtain a more accurate evaluation.